Hello, welcome to, Hello, and welcome to this press conference of this afternoon. The big bubble in the sky, our solar system viewed from the inside by Stamatios Krimigis from the Academy of Athens, and I think also from Johns Hopkins and the US. Please go ahead.
Thank you very much. What I'm going to talk about today is how we have been able for the first time to make an image of the distant solar system from inside the solar system. And to do so, we used a new technique with an instrument that has been in orbit around the planet Saturn for the past 7 years or so. And just to give you an overview of where we are, here is the sun at the center with the planets surrounding it. And Saturn is here, where the spacecraft Cassini is orbiting the planet. And this is a sort of an expanded view of where Saturn is, with its moons of Mimas and Tethys and Rhea and Titan, and the spacecraft Cassini that is often outside the orbits of these moons and often looking at the rest of the sky. And I wasn't quite finished with that. At the rest of the sky, and when it does go away from Saturn at apoapsis, then it can see the whole celestial sphere, and as it does so, it presumably can see where our solar system is moving with respect to the local interstellar cloud, the galaxy. And it takes images, but it doesn't take images with photons, which is the normal way of taking images, but it does so with a new technique which is called energetic neutral atoms. You might say, what kind of images can you take with atoms? If you build the right camera, you can. And this particular image shows the principle of where we have a particle that is gyrating about a magnetic field. This could be oxygen or protons. And then it has a collision with a neutral atom. So you have an energetic ion and a cold neutral, and when it does that, it steers an electron. And when it steers an electron, it becomes neutralized, and now it can just take off from the system just like a photon, just like what we use to make pictures with. And if you have the right camera, then you can actually find out where it came from. And that's the principle of energetic neutral atom imaging. So, for many years, we thought that there are many of these ions where the solar wind ends, the gas that propagates from the sun at a speed of about 1.5 million kilometers per hour, and interstellar space begins. And there is also neutral gas from interstellar medium in that location. And these ions that turns out are very hot, exchange electrons. And when they do, just like they come into the heliosphere unimpeded by the magnetic field. And here we see the Saturn. We look out and we see these atoms coming. And because we can look all over the sky, then we can make an image of those. Now, what we knew until a few months ago was that we had the so-called image of the heliosphere, or our concept of the heliosphere, because it was never an image, and we had sent out Voyager 1 in the northern ecliptic, and then Voyager 2 in the southern ecliptic. And in the last 5 years, we have crossed through what is called the termination shock. That's where the solar wind that is emanating from the sun finally begins to lose its organization and becomes disorganized, and it slows down, and from about 100 and, as I said, 1.5 million kilometers per hour, all of a sudden its speed drops down to a few thousand kilometers per hour. Still pretty fast, but it's very much less than what it was before. So we now have measurements with Voyager 1 and Voyager 2, and I happen to be the principal investigator of one of the instruments on Voyager 1 and on Voyager 2 that are making these measurements at the distance, and the distance is not given here, but the distance is 100 times as far from the sun as the Earth is, 100 astronomical units. So when but we have never really seen this. This was just a concept. And we think that the solar system moves in this direction against a wind that is coming from the galaxies. And therefore, we have a shape, it's like a comet tail. So when we looked with these energetic neutral atoms, and what we found with Cassini is that this was not like a comet at all. It was a big belt around the sky. It was very broad. It extended to north and south ecliptic as well, and it had some minima at various areas. And in fact, when we sketched the galactic equator here, we found out that it seemed to be sort of enveloped by this belt. And when we replotted the data in terms of galactic coordinates, we found out that this broad belt of these hot ions that turned into neutrals by charge exchange that we were able to image, and that were arriving where Cassini is, in the vicinity of Saturn, were coming mostly around the galactic equator, plus or minus 40 or 50 degrees. So what other things can we do with that? Well, the first thing that we know is that ions are gyrating around a magnetic field. And the galactic magnetic field, which was guessed at in the past and indirectly measured by the polarization of atoms, and I don't want to go into that, was thought to have a direction which was, as noted here, the interstellar magnetic field. And we didn't know much about the magnitude. Now, with the measurement, however, that we made, oops, sorry about that, what you see is that the symmetry axis of this belt is here. So we think that the galactic magnetic field is actually pointing in this direction as opposed to that. And the old one is what I just pointed out. That's where we thought it was. That's where we now believe it is. And we give here the longitude and the latitude in ecliptic coordinates. Okay, so what does all of this tell us? Is the heliosphere still the same, what I showed you before? We think that this part is very iffy, that it doesn't look like a comet going through the galaxy anymore. It's, in fact, when we project the image that we saw on where the Voyagers are now located, which is here is Voyager 1, here is Voyager 2, here is where all these particles back and forth congregate, we think that it may be more like a bubble, perhaps somewhat elongated, but a bubble nevertheless. And in fact, we have made some calculations, and we estimate that the thickness between the so-called termination shock and the edge where Voyager is going to be truly out into the interstellar space, it's about 50 astronomical units. 50 astronomical units is 50 times the distance between the Sun and the Earth, 7.5 billion kilometers thick. So these are big numbers. We expect that Voyager will probably get out into, pardon me, so we have done that yet. I didn't intend to. Back. I hope I didn't hear it. I plan to show you a video, and what is going to show when it does its thing is that we move from the Sun to the outer solar system. We see the solar wind, and then at some point you begin to see this interstellar magnetic field now essentially become deformed around this bubble of big plasma that we have discovered with Cassini. And let me see if I can escape this. Hope it doesn't play through. Sorry about that. Computers do things like that now and then. I apologize. Let me see this, and then I will redo it. Okay, now it plays. So what you see is essentially we're going past the planets, and you see this bubble form, and soon you will begin to see how it moves through the galaxy, and you see these lines that move to the right show how this bubble of gas displaces the interstellar magnetic field, and it makes it form a bottle around this bubble, and it weakens the magnetic field. So you can think of it as if a boa constrictor swallowed a big mouse, or maybe a small animal, and it moves right through, and you can see the bubble sort of move down the tail of the boa. That is an image that our solar system forms as it moves through the interstellar medium now. Before, we thought that it simply confronted the galactic wind, and the back of it was just basically empty, but just like a comet is as it goes through our solar system and it approaches the Sun. So that is what we have found out. This theory of what the solar system shape is has been with us for 50 years. It was put together by a visionary physicist by the name of Eugene Parker from the University of Chicago, who, however, did consider the case of a very strong interstellar magnetic field and did predict that it would be a bubble. But most people were very comfortable with the idea of a comet moving through the interstellar medium, and that was the idea that prevailed. He worked out both cases. But the one that prevailed was the one that was the simplest one to visualize because of the comet analogy. Nobody thought about the bubble. And 50 years later, we now know that is the real case. Thank you.
Thank you very much, Stamatios. Is there anyone who wants to ask?
Randy Shostak, reporter with EOS, the newspaper of the American
Yes,
Geosciences.
sir.
This is fascinating. I'm just wondering if you can tell me a little bit about what prompted all of this work, what prompted you to look into this,
That's an excellent question, because we have been at Saturn now for about 6 years. And before that, we had the cruise of Cassini from Earth to Saturn, which went from October of 97 through July of 2004. This instrument was designed to look at the magnetosphere, the magnetic envelope of Saturn. And when we did get there, we were fascinated with the terrific variability of the gas of ions and electrons, the plasma, that was trapped in the magnetic field of the planet. And we found out that it rotated with the planet. We found out that it had huge explosions, and all of a sudden it would start rotating with the planet, and then it would disappear, and then it would reappear. So we were so consumed by the phenomenology of what we were seeing around the magnetosphere of Saturn that we put this in the back burner and didn't bother to look at the data, as simple as that. And then there was the talk about a specific mission that we very much applauded, called IBEX, Interstellar Boundary Explorer, that was to be put in orbit around Earth to look at just that, this particular phenomenon. And we said, aha, we have all this data sitting around, and we have never looked at it. And we did, and sure enough, all of this came out. And we agreed to have a joint publication on the first report with IBEX that appeared in Science last November. But of course, we are doing a lot of work. There is a lot of new stuff that is coming out, and we are going to be reporting on some of this at the meeting here on Friday. So we could have known that 4 years ago at least.
What kind of new stuff? I couldn't hear my from Nature. I won't be here on Friday. It's really fascinating. So can you say a few things about what kind of new things and discoveries you'll be talking about on Friday?
Yes, of course. And I should add, by the way, that one of the discoveries that we made was a ring current around Saturn, which we published in Nature 2.5 years ago. But now we've turned our attention to these phenomena. And one of the things that's a key question is if this is really the interaction between our solar system and the galaxy, it means that it has to be fairly stable. In other words, it cannot be dependent on the activity of the sun. And so the first thing that we wanted to look at was whether there is any time variability. Does it look the same this year as it did last year? And that's what we're going to talk about on Friday, and the time variability. So that is a principal thing. The other thing that we will be talking about is also what is the magnitude of the interstellar magnetic field, because we have a way of computing that now that is fairly solid, and we can give the magnitude as well as the direction that I pointed out from our data. So these are some of the new things that we'll be talking about.
Thank you.
I'd like to follow up on that and just sort of see if you can stretch out your response a little bit and tell me what other kinds of things can you do with this? What other kinds of things can you do?
With this particular data set?
Yes.
Well, right now, the only anchor that we have, the connection between what we see from these atoms that come from a very long distance away, from 16 and 17 billion kilometers to 1.5 billion kilometers where Saturn is the measurement in place of the Voyager 1 and Voyager 2 data. So we can take the pixel in the sky where Voyager 1 is and relate it directly to what we see with these energetic neutral atoms. This is the only way that we can establish that these atoms are coming from that far away. If we did not have Voyager there, they could have been coming from, you know, Alpha Centauri for all we know. I'm joking, of course. But it's our ground truth in quotation marks that's provided by the Voyager data. And parenthetically, I might add that, you know, a few years ago there were some personnel at NASA headquarters that said, "Oh, why are we looking at Voyagers? We've been with them for 30 years. There's no need to continue tracking them." Where they're the only observers, if you like, sent out by humankind that is that far out, and we're not likely to get to that distance to at least in the next 30 or 40 years. So it's a terrific resource, and it keeps, the Voyagers keep discovering new information. And this is only the latest sense of serendipity that occurred that would not have been possible otherwise without the Voyager data.
All right. If there are no more questions, thank you very much, Stamatios, for this very exciting piece of information.
Thank you for inviting me.